Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon, but it's kind of got to make you laugh to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. Everything in our universe seems perfect. There are laws governing the entire universe, but certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie? It's merely a construct of the human brain. This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down to find out what on earth is wrong with gravity. We need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. There's a problem with Newton's theory of gravity, and that's that it just allows us to predict how things move under its influence. It doesn't say anything about why gravity exists or even how it works. It just allows you to calculate things. Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets, and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God. In the vast universe that surrounds us, there are mysteries waiting to be covered. Among these mysteries are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century, when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredible speed, close to the speed of light. Inside this spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who's not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a longer diagonal path. Now here's where it gets interesting. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. It's not just a concept. Experiments have confirmed these relativistic effects. For example, particles in particle accelerators, like the Large Hadron Collider, can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens the door to a world where time is not a constant, where it can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the realization that the universe operates in ways far beyond our common experience. Einstein's special theory of relativity, introduced in 1905, reshaped our understanding of the universe's fabric, particularly in terms of time and motion. This theory, in its essence, reveals that the laws of physics apply uniformly for all non-accelerating observers irrespective of their motion. To understand the special theory of relativity better, let's break down its core concepts. One of the fundamental ideas of the special theory of relativity is that the speed of light is the same for everyone, regardless of their motion. Whether you're standing still or moving at a high speed, light always appears to travel at the same constant speed, approximately 299,792,458 meters per second. This concept goes against our everyday experience, where speeds usually add up when we're in motion. It's as if the universe has a built-in speed limit, and that speed is the speed of light. In special relativity, what we consider simultaneous events may not be simultaneous for everyone. If two events occur at different locations and you're in motion relative to those events, what you see as happening at the same time may not be simultaneous for someone else at a different vantage point. This seemingly strange idea challenges our conventional notion of time. The concept of time dilation is one of the most fascinating and practical implications of the theory. As mentioned in the first section, time can slow down or dilate depending on your motion. The faster you move, the slower time appears to pass for you relative to the stationary observer. This effect becomes more pronounced as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their Earth-bound sibling. This phenomenon, often referred to as the twin paradox, is a real consequence of time dilation. The reason behind this peculiar behavior lies in the invariance of the speed of light. As the space-traveling twin accelerates to a high speed, the ticking of their clock appears normal to them. However, to an observer on Earth, the space-traveling twin's clock appears to slow down because the space-traveling twin is moving relative to the Earth. Another consequence of special relativity is length contraction. As an object moves at high speeds, its length in the direction of motion appears shorter to the stationary observer. This effect is minuscule at everyday speeds, but becomes more noticeable as an object approaches the speed of light. One of the most famous equations in physics, E equals mc²2 is a direct outcome of special relativity. This equation states that energy and mass are interchangeable. It means that mass can be converted into energy and vice versa. This principle is fundamental in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity isn't just a theoretical concept, it has real-world applications. For example, GPS systems rely on the precise timing of signals from satellites. However, because these satellites are moving relative to us, the time dilation effect comes into play. If the effects of special relativity were not accounted for in the GPS calculations, our navigation systems would be significantly less accurate. The special theory of relativity forces us to reconsider our intuitive notions of time and space. It demonstrates that the universe operates in ways that defy everyday experience. Time is not an absolute concept, but is relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas that have been confirmed by numerous experiments. Now, let's delve into the general theory of relativity, another groundbreaking concept put forward by Albert Einstein in 1915. This theory takes us into the realm of gravity, revealing a profound connection between gravity and the very fabric of the universe. At its core, the general theory of relativity challenges the classical concept of gravity as a force that acts at a distance between masses. Instead, it presents gravity as a consequence of the curvature of space-time. This idea is simpler than it may sound. To understand general relativity, we need to think of the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this four-dimensional space-time, massive objects such as stars, planets, and even you cause the fabric of spacetime to curve around them. This curvature is what we perceive as gravity. Imagine spacetime as a vast, flexible fabric. A massive object like the Earth creates a dimple in this fabric. When you place a smaller object, like a ball, near the Earth, it rolls towards the dimple. This is analogous to what happens when an object falls under the influence of gravity. It's not a mysterious force, it's simply following the curvature of spacetime. General relativity provides a powerful explanation for the motion of celestial bodies in our solar system. It correctly predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an attractive force didn't fully account for these orbital motions, but the concept of curved spacetime does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight by the Sun's gravity. According to the theory, the massive Sun curves spacetime, causing the path of light from distant stars to bend as it passes near the Sun. Eddington's observations matched Einstein's predictions precisely, providing strong evidence for the theory. General relativity also explains phenomena such as gravitational time dilation. Just as time slows down for an object moving at high speeds, it also slows down in the presence of strong gravitational fields. This effect is particularly pronounced near massive objects like black holes. To an observer far from the gravitational source, time appears to tick more slowly near the source. Speaking of black holes, these are among the most extreme predictions of general relativity. A black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape from it. The boundary around a black hole, known as the event horizon, marks the point of no return. Once an object crosses this boundary, it is inexorably drawn towards the singularity, a point of infinite density at the center of the black hole. The concept of black holes, once purely theoretical, has been supported by extensive observational evidence, including the detection of gravitational waves. Gravitational waves are ripples in the fabric of spacetime, generated by the acceleration of massive objects, such as colliding black holes or neutron stars. The discovery of these waves by LIGO and Virgo detectors in 2015 provided further confirmation of general relativity and opened a new window into the cosmos. As with special relativity, general relativity has practical applications in our daily lives. For instance, the precise functioning of GPS systems relies on accounting for both the relativistic effects of motion and gravity. Without these corrections, our navigation systems would be significantly less accurate. General relativity, like special relativity, challenges our everyday intuition. It shows us that gravity is not an invisible force, but a manifestation of the curvature of spacetime. This profound understanding of gravity has transformed our view of the universe, leading to discoveries that